Hello, and welcome to the Engines and Powerplant lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics: 737NG Engine System Overview, Engine Fuel System Overview, Engine Oil System, Starting and Ignition Procedures, and Thrust Reversers. We will not be discussing auto thrust in this lesson, as we have comprehensively explained it in the autoflight lesson. The 737NG is powered by two CFM56 Type 7B engines that provide power to propel the aircraft forward and also to power the following aircraft systems: electric, pneumatic, and hydraulic. The 737 hydraulic, air, and electric systems lessons include comprehensive discussion about the relationship between the engines and the respective aircraft system, so we won't be discussing those relationships here. To create the required forward-pushing force or thrust, each engine has the following main components: fan, booster or low-pressure compressor, high-pressure compressor, combustion chamber, high-pressure turbine, low-pressure turbine, and exhaust. The fan has 24 fan blades that spin together counterclockwise to increase the speed of the air entering into the engine. A splitter divides this air into two types: primary airflow and secondary airflow. The primary airflow, which is about 20% of the total air entering the engine, enters the engine core and goes through the rest of the components that we mentioned previously. The secondary airflow bypasses the engine assembly and is rushed out of the engine at a fast speed. The ratio between secondary and primary airflows is known as bypass ratio. The CFM56-7B is a high bypass ratio engine. The higher the bypass ratio, the better fuel efficiency is achieved and a lower engine noise is produced. The fan essentially works like a light aircraft propeller. However, it's designed to perform considerably better at higher altitudes and airspeeds. After passing through the fan, the high and low pressure compressors compress the air to increase its pressure and temperature. The low pressure compressor has 3 stages of compression, whereas the high pressure compressor has 9 stages. After the air has passed through all 12 stages, its temperature is roughly 450 degrees Celsius. Moving on, the combustion chamber takes this dense, compressed air from the compressors and also receives fuel from a series of fuel nozzles. These two elements are joined to create a fuel-air mixture that is burnt in order to make hot gases. At this point, the air-fuel mixture temperature will have increased to roughly 1700 degrees Celsius. Because the hot gases in the combustion chamber carry so much thermal energy, they move further to the high-pressure turbine. This is a single-stage turbine that converts some of that thermal energy into mechanical energy in order to move the high-pressure compressors. The high-pressure turbine is linked to the high-pressure compressors with a shaft. The high-pressure shaft also turns an accessory gearbox that holds and operates the airplane and engine accessories. Some of these are the hydraulic pumps, sensors, oil filters, etc. The remaining thermal energy from the hot gases is also converted into mechanical energy by the low-pressure turbine. This turbine has 4 stages and moves the low-pressure compressors, or booster, and also turns the engine fan. The fan, booster, and low-pressure turbine are linked with a shaft that is mechanically independent from the high-pressure shaft we mentioned earlier. A surrounding engine cowling protects all the engine components. This cowling has an aerodynamically smooth surface in order to minimize drag. Access doors are available in order to perform maintenance. In addition, in the event of a foreign object being ingested into the machine, this cowling works to contain engine components if there is a breakup. Flying engine parts don't bode well for anything on the aircraft, including passengers. To put things in simple terms, the secondary and primary bypass air work in conjunction to create thrust, or fast-moving air, that drives the aircraft forward. This works in a carefully synchronized mechanical harmony, considering fuel efficiency and low noise print along the way. Worth mentioning at this point, there are several controls and indications associated to the engine system on the 737 NG. We'll be discussing these progressively throughout this lesson. However, the engine indicating system can be grouped into two categories: primary engine indications and secondary engine indications. The primary engine indications are those of immediate importance to the flight crew. They are low pressure shaft speed, or N1, exhaust gas temperature, or EGT, fuel flow, fuel quantity per tank, total air temperature, and active thrust mode. The secondary engine indications are not required to be constantly monitored. However, they're still significantly important. They are high pressure shaft speed, or N2, oil pressure, oil temperature, oil quantity, and engine vibration level. We don't expect you to know what these are right now, as we'll be teaching them throughout this lesson and continually as we fly the aircraft. Much of what happens with the engines can be categorized as seeing is believing, so that's exactly what we'll do throughout your training. Engines on the 737 ideally work with Jet A or Jet A1 fuel supplied from the wing tanks and center tank. This fuel is pressurized and is boosted into the engine system with booster fuel pumps. Immediately outboard of each engine strut, there are engine fuel spar valves. These fuel spar valves permit fuel flow from the engine feed system towards the engine fuel supply systems. There is one fuel spar valve on each wing. The fuel spar valves are controlled with the engine start levers located below the throttles on the control stand. There are two start levers, one for each engine. Start levers are used to start and shut down the related engine. Each start lever has the following positions. Cutoff. This closes the fuel spar shutoff valve, prevents fuel from flowing into the engine fuel supply systems, and also de-energizes the engine ignition system. The ignition system will be discussed further along in this lesson. Idle. This position electrically opens the fuel spar shutoff valve and also opens another engine-mounted fuel shutoff valve. When the start levers are placed in idle, the ignition system is also energized. Moving on, once the fuel is passed through the fuel spar shutoff valves and is free to flow into the engines, it passes through four important stages: fuel pump first stage, fuel oil heat exchanging, fuel filtering, fuel pump second stage. Both stages of the fuel pumps are used to increase the fuel's metered pressure in order to deliver a constant high-pressure flow into the engine fuel system. Following the fuel pumps, it's important to know about the fuel oil heat exchangers. In the 737 NG, fuel may be as cold as negative 43 degrees Celsius. Naturally, it takes a lot of energy to bring its temperature up to the whopping 1700 degrees Celsius that is achieved during the engine combustion process. On the other hand, in order to lubricate moving parts, engines have oil. This oil gets very hot during operation and it must be cooled. The best solution to this problem is to exchange thermal energy between hot oil and cold fuel so that oil becomes colder and fuel becomes hotter. This occurs in two stages. First, the fuel passes through the Integrated Drive Generator, IDG, oil heat exchanger. And secondly, it passes through the main engine oil heat exchanger. The IDG will be explained in another lesson. At this point, just note that the fuel is super cold and needs to be warmed up. Now, time for filtering. Any form of fuel contamination is bad. It makes combustion difficult and subsequently decreases the engine life. In some cases, when the fuel is excessively contaminated, it may even lead to an immediate engine failure. To prevent this, fuel is filtered to minimize the presence of contaminants. If contamination clogs the filter, a bypass valve opens and fuel does not go through the filter before it continues towards the engine, ensuring that fuel flow is not sacrificed. It's better to have contaminated fuel temporarily than no fuel at all. Following all the components we've discussed, fuel finally goes through a hydromechanical unit. The HMU will not be covered in this lesson as it's discussed in the fuel system lesson. However, inside the HMU, fuel is metered and fuel flow is controlled by an electronic engine control, or EEC. The EEC uses analog and digital data to calculate the required engine fuel and controls output to operate the engine through the fuel supply that the HMU provides. The mass flow of fuel that goes from these components into the fuel nozzles in the engine is measured by a transmitter that provides fuel flow indication. Fuel flow and fuel used are displayed as secondary engine indications in the display units. There is a fuel flow switch in the center forward panel that has 3 positions. Reset shows fuel used, resets it to 0, and then displays fuel flow. Used shows fuel used since last reset and then displays fuel flow. Rate simply displays fuel flow to both engines. You may be wondering, why is the electronic engine control so important? The EEC calculates thrust with ambient pressure, ambient temperature, and N1 speed. It senses the actual N1 compared to commanded N1 and makes the necessary change in fuel flow. The EEC is also in charge of keeping N2 and fuel flow readings within limits. The EEC may operate in 3 modes: normal mode, soft alternate mode, and hard alternate mode. You may also be wondering, does the exact same engine provide power to all variants of the 737NG? The answer is yes. However, each individual aircraft type, like the 737-600 or 737-800, have specific thrust configurations and a maximum thrust setting that is outlined and configured with an engine identification plug that specifies each thrust rating for each individual variant of the 737NG. Let's refer back to the primary and secondary engine indications